When the soil conditions are not favorable for a proposed geotechnical project, there are few options. The obvious ones are to relocate the project to a site with better soil conditions, replacing the problem soil with better soil, etc. We can also improve the existing ground through one of the many ground improvement techniques. The simplest of these is compaction. Poor ground conditions include soft clays, sanitary landfills, karst terrain, etc. They can lead to high settlements, possible failures, and also high seepage. Ground improvement, in the form of compaction, would help here. In compaction, we add water to act as a lubricant between the soil grains to facilitate the compaction process, and apply some external energy in the form of a force, impact or vibration to densify the soil. See the stress-strain plots of the same soil uncompacted and compacted. Due to compaction, void ratio decreases and dry density increases. In addition, the strength and stiffness increase and permeability decreases. Here we mix the soil at few different moisture contents and apply a certain compactive effort to compact the soil in a cylindrical mold. The plot of dry density or dry unit weight versus moisture content gives us the compaction curve. Here you can see the compaction hammers and molds used in the laboratory for compacting a soil using a specific compactive effort. The hammer assembly consists of a standard mass that is raised and dropped over a fixed height, applying a certain energy to the soil in the mold for each blow. In a typical compaction curve, the dry density or unit weight peaks at a certain moisture content known as the optimum moisture content. The corresponding dry unit weight is called the maximum dry unit weight. The best geotechnical properties are obtained when a soil is compacted near the optimum moisture content, giving the soil high strength and stiffness, and low permeability. When a soil is compacted at a moisture content less or more than the optimum moisture content, It is known as compacting dry or wet of optimum, respectively. Let's see what happens when we increase the compactive effort. Here, we try 3 different compactive efforts on the same soil and see that the compaction curve moves upwards and to the left when the compactive effort is increased. That means, with increasing compactive effort, the maximum dry density increases and the optimum moisture content decreases. Here, you can see what happens to the relative proportions of the 3 phases with increasing moisture content. We keep the total volume constant at all moisture contents. The porosity and the void ratio are the minimum at the optimum moisture content. On the dry side, there is lot of air in the voids. On the wet side, there is lot of water in the voids. Let's look at the dry unit weight versus moisture content space for a soil where the specific gravity of the soil grains is 2.72. We select a point randomly where the moisture content is 14.3% and dry unit weight is 17.2 kN per cubic meter. From the phase relations, we can find the degree of saturation S as 70.6%. That is, every point on this space has a specific value for the degree of saturation. In the dry unit weight versus moisture content space, we can locate the points where, for example, degree of saturation is 70% and establish the contour. We can do the same for any value of the degree of saturation and hence develop the contours for 60%, 70%, 80%, and so on. The one corresponding to S equals 100% is called the zero air void curve. How do we develop the contours for different values of S? From the phase relations, we express the dry unit weight in terms of Gs, W and S for a specific value of Gs and S. Substituting different values of W, the corresponding dry unit weights can be determined. The zero air void curve divides the dry unit weight versus moisture content space into 2 zones. The region to the left is where S is less than 100% and the on the right S is greater than 100%, which is not possible. On the zero air void curve, S equals 100%. That means, all compaction test points must lie to the left of the zero air void curve. It is always a good practice to include the zero air void curve along with the compaction curves as a good check. Air content of a compacted soil is defined as the ratio of the air volume to the total volume, VA on VT. Mostly in European countries, they use air content contours instead of degree of saturation contours. Again, using phase relationships, we can develop these contours. Soil is compacted in layers in the field. The compacted layers are called lifts. In the laboratory also, we compact the soil in layers, in a cylindrical mold, using a compaction hammer that consists of a standard weight falling over a certain height, imparting some compaction energy to the soil in the mold. We have two different hammers and two different molds for the laboratory compaction. We commonly use two different compactive efforts, known as standard and modified Proctor efforts. The compaction mold we use generally has a capacity of about 1000 ml. Only when we have a large quantity of gravels present, we use a larger mold volume of slightly more than 2000 ml. You will find this equation very useful to convert bulk unit weight to dry unit weight and other way around. Here, you can see the material being brought from the burrow, water being sprayed prior to the compaction, and soil being spread. There are a few different types of rollers for compaction in the field. Here, you can see a smooth-wheeled roller used for finishing job and a sheep's foot roller used mainly in clays. The protruding feet in a sheep's foot roller get into the clay, knead, and walk out. Impact roller can have 3, 4, or 5 sides. Here is one with 3 sides. Every time a side comes into contact with the ground, it gives an impact energy of up to 100 kilojoules to the ground. See how the same side looks before and after the earthworks. There are 2 different ways of telling the contractor how the compaction is to be done. They are method specification and end product specification. In method specification, we specify every detail such as roller type, number of passes, lift thickness, and moisture content, and take the responsibility for the outcome. In end product specification, we specify what we require as the end product and let the contractor select the variables and take the responsibility for the outcome. We generally measure the moisture content and dry unit weight at few randomly selected locations in the compacted ground to ensure the compaction meets the specifications. You can see from the table that typically we like to see at least 90% of the maximum dry unit weight from a modified Proctor compaction test. We stay around plus or minus 2% from the optimum moisture content. Once the compaction is done by the contractor, it is necessary to carry out some spot checks at random locations to ensure the compaction is carried out properly, meeting the specifications. We have been doing a sand cone test, also called a field density test, to measure dry unit weight and moisture content. These nuclear density meters have become very popular. California bearing ratio or CBR is widely used as a measure of the strength or stiffness of a compacted earthwork. Here, the compacted earthwork is compared against a reference material, which is a compacted crushed rock, assigned a CBR rating of 100. A standard piston is pushed into the compacted earthwork in a cylindrical mold and the resistance to penetration is compared at 2.5 mm and 5.0 mm penetrations. In clays, whether the compaction is carried out dry or wet of optimum can make a big difference in the geotechnical behavior of the compacted soil. Depending on the situation, we select the target moisture content right and specify a narrow range with 1 or 2% on either side. This is from Townsville, Australia. A heavy weight of about 10 to 30 tons is lifted by a height of 10 to 30 meters and dropped, repeatedly, pounding the ground. Dynamic compaction works well on karst topography with sinkhole caverns underneath, sanitary landfills and uncontrolled fills.